Thanks to the organizers for inviting me and organizing this wonderful conference. And thank you to all of you as well who are attending the session. So what I'm going to talk about in this talk is some work that is extremely important, which is responsible AI. But this could mean different things. So what do I specifically, what am I focusing on in this talk is a topic known as distribution shift. Pittsburgh actually has multiple self-driving car startups. I think at last count we had more than 5 that were unicorns. And part of the reason for that is that Pittsburgh is what one might affectionately call an adversarial driving environment, mostly for weather reasons. So it is cloudy for one, it is hilly for another. Okay. Now, why is this relevant? It's relevant because imagine that I train an autonomous car system in California. So let's just say I train it in Sunnyvale, which is sunny, it's in the name, and flat. And then I deploy the system in Pittsburgh, which is perhaps not as sunny and not as flat. Then a very important question is, would the autonomous AI, autonomous car system, function as well? This is what we call distribution shift, where the environment in which we deploy the AI system is different from the environment in which we train the AI system. Now, the thing is that even though a lot of the way we develop AI systems is to assume that the training and the deployed environments are roughly similar, in the real world, that does not happen. Okay? One particular problem that has implications for fairness as well as tail risk, as I'll talk about, is known as subpopulation shift. This is where both the training as well as the deployed environments consist of the same set of subpopulations, but different mixtures of these subpopulations. So what do I mean by that? Imagine that the data only consists of 2 subpopulations, the reds and the blues, okay? And imagine that the training environment has 75% blues and 25% reds. Okay, so more blues than reds. But imagine that the deployed environment has the fractions reversed in the sense that there are 75% reds and 25% blues. Now, why does this matter? It matters because imagine that I'm training an AI that does well on the training distribution. Okay, the training distribution, again, is the data that is used to train the AI. Now, what do we look for when we train the AI? We look for a model, a system that performs well in the training environment. But what does that really mean? It means that it has to perform well when there are 75% blues and 25% reds. So what will basically happen is that, at least implicitly, the system will prioritize performance on blues because most of the data in the training environment come from blues. But then in the test or deployed environment, you have a lot more reds than blues, right? So clearly the AI system would be suboptimal for the specific deployed environment in which it is deployed. This is a problem, right? So how do we fix this is a really important question if you want to deploy successful AI. Now, these are questions that come up even for very simple things that, for instance, polling agencies will be concerned with, where they would poll people's preferences, but the polling subpopulations would be different from perhaps the entire population whose preferences they care about, right? So they try to adjust for these based on various guesses. But what if we have no idea about the subpopulations that are of interest. In particular, we may want our models to perform well on arbitrary subpopulations. Now, why might that be of relevance? Think again about the autonomous car. So what do I mean by a subpopulation? It's really a subset of terrains, a subset of weather conditions, right? Instead of individual people, like in a polling context here, we have different scenarios, driving scenarios. And do we want an autonomous car or any autonomous driving system that will just arbitrarily crash for some small subset of weather or terrain scenarios? We would not, right? We would prefer an AI system that would take care of such tail risks. So there should not be any particular subpopulation that would have a high tail risk. This is exactly the question of being robust to arbitrary subpopulations. Now, how might I train a model that can be robust to about in particular populations that we don't even know about, right? So when I'm training an autonomous car, I don't know of weather, terrain, goodness what else, where this model might potentially perform catastrophically, right? So how might I train a model then to perform well with respect to that? So it turns out that there are a few approaches that try to do this. But before that, I want to first underline the basic approach, that is the standard approach that is used in ML and AI, which is called ERM, for expected risk minimization. What this does is that it minimizes the risk of your model on average. So that's basically where the expected comes in, okay? So imagine that when I'm training an autonomous car, it is, let's just imagine, trained on 1 million different scenarios. I want to train a model that would perform well on average over these 1 million scenarios. That's how we train our models, okay? But if you care about tail risk, on average is perhaps not that great, right? There's this famous quote, I forget by who, which says that imagine there is a person who is 6 feet tall, okay, and he wants to cross a river that is 5 feet on average. Do you think that this 6 foot tall person would not drown if they cross this river that is 5 feet on average? Perhaps they might drown if there's a small portion of the river that is 7 feet or 8 feet or 10 feet deep, right? So on average is not as helpful as ensuring that there is no small portion of the data where you would encounter catastrophic risk. So there are two approaches which when we are developing AI systems we follow, called DRO and CVAR. DRO stands for distributionally robust optimization, where at a high level what you do is that instead of training models that perform well on average over your training scenarios, you train your models to perform well on average over a small neighborhood of your training data. In other words, you take your training scenarios and you change it a little bit. Okay, so you look at various small changes to your training scenarios, and then I train my model to perform well on average. So this is a reasonable approach, right? But perhaps even this might not give you the confidence of ensuring performance on arbitrary subpopulations, for which you might then prefer CVAR, for conditional value at risk, where what you do is say that for any model, the way I'm going to evaluate the model is to check for its worst performing subset of scenarios. So the worst performing subset would be different for different models, but that's what I'm going to test the model on. Okay, imagine that, for instance, you give a test, right? And the test consists of 100 questions. Typically, the way we are evaluated on such tests is either the overall sum, or imagine the average, which is basically the same thing, right? So out of 100 questions, each with 1 point, we might be evaluated based on the overall score or perhaps the average score. But imagine that these questions are extremely important, and I would prefer not to hire somebody who would not do well on some large fraction of these questions. So then I might say I'm only going to test, the way I'm going to evaluate a person is to look at their worst 20% of questions that they have performed. Okay, so this sounds like a particularly harsh way of evaluating somebody, right? So in a lot of human contexts, we may or may not do this, but this is a way potentially to train AI models, where for that model, the way you would check its performance is to see where it performs the worst, and that's going to be the number associated with that model. So this way, I would ensure that if I'm training the model, I would ensure that it does not perform really badly on any subset of training scenarios. Okay, so basically, don't learn models on average, train models to ensure that even the worst performing subset of training scenarios is not that bad. So this is something that people realized in operations research, and we then started to use in machine learning. But then what we found was a wrinkle, okay, where these kinds of approaches like CVAR that I just talked about works for simple models like linear models and so on. But if I'm going to have extremely complicated models like gigantic deep neural networks, which is what we typically use in modern machine learning, that sounds like not that big a deal, right? The similar guarantees that you may have for linear models should also translate to more complicated models, but not so fast. What we can show is that if I have sufficiently complex models, then CVAR is no better than a model that is trained to perform well on average. And moreover, if your data quality is even modestly lower, it's actually worse for worst case or tail risk considerations compared to a model that is trained well on average. Okay, so why might this be? The reason is that the moment I go to extremely complicated models, they memorize the data. If they memorize the data, and this has been well established, that these gigantic deep neural networks, they completely memorize the data, training scenarios. So if I'm going to memorize the training scenarios, then there is no subset of training scenarios where they would perform badly, right? So it doesn't make sense to say that, oh, I'm only going to train my model to ensure that there is no subset of training scenarios where it's bad if the model is perfect on each and every training scenario, right? So in particular, so from this high level argument, you can see that, you know, if with a sufficiently complex model, CVAR is no better than ERM. Okay, so it's not really the chosen one, if you will, the moment we use our modern complex models. So what do we do for tail risk, right? Because I still want to deploy AI systems, and just because I have a system that is perfect on training scenarios, okay, so think again of an autonomous car that is trained on 1 million scenarios in Sunnyvale, that still does not mean that it'll perform well if I deploy it in Pittsburgh, right? So this is particularly the case if I'm going to use complex models. So what do we do, right? So that's a pretty damning theorem, and we showed this mathematically. So what do we do? So it turns out that there's a very, very simple approach to finesse this bottleneck, which is to use randomized predictions. Okay, so this sounds dangerous, right? Where for high stake settings, why are we thinking about things that are random? But I'll just talk about how in a lot of important settings, such a randomized strategy is actually better. But in particular here, what you can show is that a randomized predictor, in other words, its prediction is random rather than deterministic, meaning that for any particular scenario, its prediction is random. It is no longer the case that CVAR would be the same as, in other words, looking at the worst subpopulation risk is the same as average risk. Now, you might be worried about randomized predictions, right? Because an autonomous car, you don't want it to behave randomly. But from a mathematical perspective, you can think about a randomized predictor as simply consisting of multiple predictors. Okay, so this is like a multiverse. So thanks to Marvel and its multiverse saga, this is perhaps easier to describe. I can think about a randomized predictor as essentially consisting of multiple predictors, each with some weight. Okay. Now, a random predictor, what it will do is that it'll pick any one of these multiple predictors at random in proportion to its weight. But as I'll talk about in just a little bit, you can de-randomize it, where what you can do is simply take a weighted majority vote. Okay. So if I have, let's say, 1,000 different predictors, each with different votes, you could simply, you could do two things. One, I can pick a random predictor in proportion to its vote, okay, so in which case a prediction would be random, or one can show this is equivalent in some sense, that I could simply take a weighted majority vote, okay? So that's basically the way out, but it turns out that if instead of a single predictor, I have multiple predictors, then you can get, you can train a model, or rather multiple models that would perform well with respect to subpopulations. Now the question is how? How do I train these randomized, or sometimes what is also called ensemble classifiers? An ensemble because it's a collection of classifiers, not just a single predictor, but multiple predictors. So the way we approach this is to consider a zero-sum game. So think about a game where there are two players. One is the learner, us, where our goal is to learn a predictor, right? Our goal is to learn a classifier, a predictor. That's why I'm building an autonomous car. My goal is to build an autonomous car that can predict what's in front of it, right? So that's one player. Then you have an adversary, which is the environment, that is going to aim to find the worst performing subset of training scenarios for the learner. Okay, so now we have two players that are adversarial, where the learner wants to minimize their loss, right, or improve their performance, while the environment wants the learner to suffer a large loss. It wants to ensure that the learner does not perform well. And you can see that these guys are adversarial and it's zero sum. The amount that the learner gains is exactly the amount the environment loses. There are many zero sum games. For instance, if you think in terms of even simple games like rock, paper, scissors, right? One person wins only if the other person loses. So this specific game described here, we call it the CVAR game, because ultimately it is very related to the CVAR aim of ensuring models that have good performance even on small subpopulations. Now, it's all well and good to say, hey, here is a zero-sum game that seems to have a CVAR-like characteristic, but how do we solve this zero-sum game, right? So game theory, of course, goes back to the 1950s to von Neumann, and Morgenstern, where basically they came up with some simple strategies for simple games, whereas our game is sufficiently complicated because the actions by the players are sufficiently complicated. But recently, including some of our work, we have developed some very scalable approaches to solve such zero-sum games that arise in machine learning. Okay, so at a high level, without getting into the details, the mathematical details, how do we solve these zero-sum games? Each player, okay, would essentially be solving for the best action that they have seen so far, okay, while allowing for what we call entropy in choosing arbitrary actions. Okay? So think about rock, paper, scissors. Okay. Instead of just solving this game once, imagine that I solve this multiple times. Okay, so let's say you and your friend, you want to play rock, paper, scissors. Let's say you play rock, okay? Then the other person is essentially going to react to what they have seen you do so far. Right? So if you've seen rock, they may be able to react to that saying, oh, you have played rock, so let me play paper, right? But instead of just reacting exactly to your action, they could actually have a little bit of an entropy, meaning that they would allow for some small deviation from the best possible action. Okay, so maybe he not only says paper, but there is a small chance they would choose some other action. Now, the ball is back in your court, and then you would see what they played. Maybe they played paper, and then you would react to that. And this thing goes back and forth. Okay, now why is this helpful for solving zero-sum games? This is what one can show. Again, it's not obvious, but what you can show is that the different actions that each player plays over multiple rounds, you can essentially think of this as votes for the different actions, and you simply do a weighted majority vote, and this turns out to provably be close to the optimal randomized action. Okay. All to say that there are very, very scalable approaches to solve these zero-sum games, but which will give you a randomized predictor. They won't give you a deterministic predictor. They will only give you a randomized predictor. Okay, so in game theory, this is called a mixed strategy. And for games like rock, paper, scissors, the only winning thing is to essentially play a mixed strategy. So this may perhaps be extremely obvious in the case of rock, paper, scissors, because imagine that you have to decide a particular action of rock, paper, or scissors, and I'm going to evaluate you based on the worst possible outcome for you with respect to what the other person will choose, right? So in other words, if you choose rock, then I'm going to evaluate you based on the worst possible for you option that the other person might play, which would be paper, right? Which means that you would lose. So no matter what I choose, rock, paper, or scissors, the other person can always ensure that you lose, right? How can you possibly beat something like this? You can beat something like this by a randomized strategy where you don't play rock, paper, or scissors deterministically. You essentially have a distribution over actions. You are essentially going to pick a random action with equal probability of rock, paper, or scissors. This turns out to be the only winning strategy, okay, to solve these zero-sum games. And that's exactly the setting we are in, right? Except that we are not playing rock, paper, scissors. So here it's pretty obvious that a deterministic strategy will always result in us losing. But this is exactly the setting we are in, except that instead of rock, paper, scissors, we are in the CVAR game. And that's exactly what we do, okay? Where we try to come up with this randomized predictor. I want to emphasize one thing, which is that now that generative AI is everywhere, one of a very important class of approaches is actually based on solving zero-sum games, where there is a game between a generative AI that aims to generate data like images and a discriminative AI that aims to discriminate between artificially generated and real data. Okay, so in other words, if you generate really bad images, the discriminator AI will be able to quickly say, hey, this is clearly an artificially generated image, you lose. Now imagine that the generative AI has to actually fool this discriminative AI. It has to step up its game, right? So this actually lies behind at least the generative AI approaches a few years ago. Okay, so but in our case, we have the CVAR game, and we are able to come up with a very scalable algorithm called CVAR boosting. So here I want to talk a little bit about a very classical algorithm of boosting, which I want to emphasize underlies most competition winning approaches. So pretty much any Kaggle or any other data science competitions are won by ensembles, meaning collections of predictors. Okay, and the way one arrives at these collections typically involves boosting. Okay, now boosting, though usually it's not described in such terms, was actually derived as a way to solve a zero-sum game between an environment that would aim to provide samples where the model performs the worst and a learner that aims to obviously maximize its performance. This seems so similar to CVAR, right? But boosting, again, dates back to the 90s. And the resulting game-solving algorithms are actually called boosting. Why are we calling it boosting? Because the question that they wanted to solve was, if you have access only to what they call weak classifiers, where what they call weak classifiers were classifiers, predictors with large error rates that don't perform really very well. Okay, so imagine I have a pool of such bad classifiers. The question they asked is it possible to boost it to a strong classifier with near zero error rates? This sounds like alchemy, right? How can you take something that is strictly bad, okay, and somehow pull it together to get something that is much, much better? This is, you can think of it as like a wisdom of the crowds kind of intuition. And what they showed is that it is indeed possible to get a weighted ensemble of weak classifiers that will be strong, meaning that it has near zero error rates, at least on the training data. In our case, we don't care about classification error on training data. What I care about is tail risk robustness. Okay, so my definition of weak would be classifiers that are not tail risk robust. Okay, now imagine I have a pool of such classifiers that are not tail risk robust. What we show is that our zero-sum game solving algorithm boosts these to a quote-unquote strong randomized classifier that is basically a weighted ensemble of such weak classifiers. Again, what I mean by ensemble is simply a collection. You do not have a single weak classifier, you have multiple weak classifiers, each with some set of votes, okay? And my ultimate prediction is simply going to be a weighted majority vote of weak classifiers, okay? And I won't have time to go over the math, but through some very simple calculations, you can show that even though I may have classifiers with very high error rates, their weighted majority vote will be near perfect. Okay, so that, again, this is the wisdom of crowds that you may or may not have seen, and that's exactly what we're going to do here. Okay, in our algorithm. So here is just a brief vignette of the performance of our algorithm. So we compare the standard way of training models, which is ERM, which basically focuses on average risk. Okay, so the green is vanilla boosting, the classical boosting algorithm, and in green is our algorithm. It has a mouthful name, but let's just think about it as our boosting algorithm, our algorithm that optimizes for tail risk robustness. On the x-axis, this alpha is the worst, is the proportion of the data that I'm going to look at, where I'm going to look at the worst performing alpha fraction of the data. Okay, so I'm going to look at the test scenarios, but I'm only going to look at the worst performing alpha fraction. Okay, so you can imagine that if I'm only going to evaluate on the worst performing fraction, for very small alphas, the error rates will be extremely high, right? Be 100%. And in fact, if I focus on average, so these are different data sets. This is an image data set. These two are image, actually all these three are image data sets. And this is a very famous data set on an AI system that predicts recidivism for bail prediction. And what you can see is that the blue, which is the standard way of training AI models, has very high error rate. If I'm going to look at a small, the worst, let's say 30% of the data, which is super dangerous, right? So this is used for predicting whether somebody should get bail or not. And if there is some small fraction of the data, 25% of the data, where the model has an extremely high error rate, it sucks to be those 25%, right? But what we can see is that our approach, which is green, has the lowest. I should mention that the y-axis is basically the performance, the loss, the lower is better on the worst alpha fraction of the data. You can see that it's much, much better. Okay, so that's basically the CVAR approach. I also want to mention one thing, which some of you might be thinking about, which is that if I'm going to focus my attention on the worst fraction of scenarios, what if I have outliers? Then most likely those worst performing fraction are likely due to outliers, which I don't care about, right? So this is exactly what happens. Okay, so here what I'm plotting is, again, this is ERM is the standard way of training AI models, and these are two approaches for being subpopulation robust. Okay, so what you're seeing, okay, so here on the left panel, I'm actually measuring the average performance, okay, and on the right panel, I'm looking at the worst group performance, where I'm just looking at, so this is on the recidivism prediction dataset, where the group here correspond to some ethnicities specific. So essentially, I'm looking at the worst, the performance on, look at the performance on each ethnicity, and I see which group has the worst performance. So the reason we care about that is that I want to make sure that there is no group with really bad performance, right? So what you're seeing is that though these approaches are really meant to ensure that your worst subpopulation performance is not too bad, they are actually bad even for worst group performance compared to a model that is just trained to perform well on average. Why is that? The reason is that there are outliers, and when I'm training my model to perform well on worst subpopulations, they focus our attention on outliers, and hence the model is basically behaving super weirdly. So what we did was a very heuristic approach of removing outliers, and then what you see is that the green and the orange are really the models that are trained specifically focusing on tail risk. They perform much better than a model that is trained to just optimize for average risk, okay, which is a standard way of training models. So what we are finding is that removing outliers is crucial before you train your models to perform well on tail risk, okay. And that's basically one of our key insights. So let me just show you this figure, which may be the easiest to think about. Okay, the x-axis is basically, think about it as the loss. Okay, you want to train models where the loss is small. Funny thing is that in machine learning, we always talk about the loss of a machine learning model, okay, where our goal is to minimize the loss or the error or the cost. Whereas in economics, ironically, for the decimal science, they always focus on utility. So the goal is to maximize the utility, maximize the gain and whatnot. Okay. But in machine learning, we use loss. So that's what we are showing here. We want to ensure that the loss is small. Okay. So if I focus on the CVAR and DRO approaches, what they would do is they would say, instead of looking at a model whose average loss is low, they would say, oh, let me look at the portion of data where the loss is large and only compute an average with respect to that. Okay, so I would look at the data where the loss is, let's say, larger than some threshold, right? And then I would only compute the average loss here, right? So that's the approach. But the problem is that if I have some data that are outliers, then your loss will be large here, but perhaps you should not be looking at those. Okay, and so that's exactly what we do, where we look at this, remove these outliers and only focus on basically the worst performing subpopulation after removing outliers. Okay, so it's a mouthful, but we look at the worst performing best 1 minus epsilon fraction of the data. Okay, so if this is epsilon, I look at the best 1 minus epsilon fraction, and in that 1 minus epsilon fraction, I look at the worst performing alpha fraction. And this turns out to be really crucial to getting good performance. And in particular, what we find is that, for instance, let's just focus on this COMPASS data set. What we find is that ERM is basically the average, the model that is trained towards average performance. And you can see that its worst case performance in this particular case is there isn't that much of a drop, but on this particular data set, I think it's instructive. You can see that its average case performance is good, but its worst group performance is sharp drop. Okay, but if I train a model specifically to focus on tail risk, there is a modest reduction in average performance, but there is a little bit of an improvement in worst case performance, but not that much. And DORO is our approach, where you can see that its average case performance improves and its worst case performance improves. Okay, so this turns out to be really crucial when training tail risk performant models. Okay, so basically what we thought was, instead of average case performance, focus on worst subpopulation performance. But it turns out that if I'm going to use complex models, then CVAR is dangerous because you may focus on outliers, and you're actually better off using average case performance. But if you use our DORO approach, you actually get the best of both worlds. You get good tail risk performance, even while using complex models with data quality issues. Okay, so in just a couple of minutes, I also want to mention that this story for tail risk also extends to other notions of robustness. So you may have seen this question of adversarial robustness in other contexts, potentially other talks in this conference, where I can have a model that is, for instance, let's say an animal recognition AI that's very confident, or perhaps not that confident in this case, that it's a panda. I add small amount of noise so that the image looks basically the same, and it will just very confidently predict a completely different animal. Okay, and in particular, this is consequences, very important consequences for autonomous cars, because instead of detecting stop signs, if there's a small sticker on top of the stop sign, I don't want you to think about it as 100 miles per hour street sign, right? And there's been really an arms race between papers that try to come up with defenses to such adversarial, these are called adversarial attacks, in the sense of having some small changes to the input, which you can think of as small stickers pasted on stop signs, and attacks that try to actually attack your model, as well as defenses that try to defend against these models. So if somebody comes up with a better attack, somebody comes with a better defense, and this thing keeps going back and forth. But basically, this is a zero-sum game, right? Where a learner aims to learn a predictor, right? I want to predict stop signs, and an environment that is basically going to tamper with the stop signs as best as it can, okay? And if I can solve this game, which you can think of as an adversarial robustness game, then our job is done, right? And that's exactly what we do. Again, we create a weighted ensemble. Instead of a single model, we have multiple models that do a weighted majority vote. Okay, so it's a committee, and they do a weighted majority vote amongst them, and that turns out to confer robustness. Okay, so here is basically a very, very difficult example where, you know, I have, let's just say, a very nice model that performs reasonably well, more than 80% performance on a really difficult object recognition data set. But if I allow for people to tamper with the inputs, just with a small amount, there's a sharp reduction in performance, okay? So what I've done here, again, the details are not that important. These are different instantiations of our boosting algorithm. What you find is that these are different iterations where I'm adding more and more ensemble members. Just by adding, let's just say 5 ensemble members, you basically increase the performance by 10%. Okay, so this is just what I wanted to emphasize, that, you know, obviously the larger the committee, the better your performance. But even with a small committee of 5 members, you boost your performance from 50% to close to 55%. Okay, so I know I've run out of time, so I just want to mention that in a lot of responsible AI settings, we are essentially can cast the optimal thing to do as solving a zero-sum game, which allows us to boost models that are not responsible to models that are responsible, but where instead of a single model, I have a committee of models. So you can think of this as robustness of crowds. And that turns out to provably and practically allows us to achieve robustness across different notions of robustness. Okay. So let me just stop there and just see if there are any questions. Thanks for listening.
Excuse me. It looks like we have a couple questions here in the GoToWebinar chat. The first one is, can you explain no tail risk robust?
Right. So tail risk robustness is basically performance in the worst performing subpopulation. If in the context of an autonomous car, so tail here is with respect to the tail of the loss distribution. Okay, where think about different scenarios. Let's think about the autonomous car. Let's think about different weather scenarios, each of which would incur some loss. Okay, so hopefully most scenarios the loss is 0, right? The car is not crashing. But there could be some scenarios where the loss is really bad. And so if I look at the loss distribution, the tail of the loss distribution, where the loss is extremely large, that's what I mean by the tail risks. And I want to be robust to those, meaning that I don't want models that have large tail risks. So that's what I mean there. Then there's another question on what was alpha measuring in the grid of charts? Is it a learning rate or something to do with the subpopulations? It was something to do with the subpopulation. So alpha there was the worst, was a fraction of the worst subpopulation. So in other words, if alpha is 0.2, I would look at the worst performing 20% of the population. So that's what alpha meant there.
We also have a question on the live.odsc.com platform. It seems like you'd want to do some EDA on those outliers and understand if they have anything in common. For example, you may define your groups based on ethnicity, but maybe these so-called outliers are female minorities or LGBTQ individuals.
That's right. So the ideal thing is to see if the outliers are actually outliers, right? So what we want to ensure, and that's definitely a very good point, that you don't want to remove points that actually correspond to importance of populations, right? That's certainly a very, very tricky question, but essentially you can think of that as highlighting the importance of doing outlier detection before you do before you focus on worst subpopulations. If you don't have any outliers, then that's great, but we know that real world data always has outliers, right? But I absolutely, you make a very good point, which is that if our outlier detection is faulty, then we might be throwing out data that actually corresponds to an importance of population, and we don't want to do that, right? So that's certainly a very, very important question. So we actually have some work, some well-regarded work on how do you do outlier detection, again, in a provable and scalable way. And one should use those strategies. Certainly a very important point.